Atomic spectra uncertainties. A certain atom has an energy level 2.58 electron volts above the ground level. Once excited to this level, the atom remains in this level for 1.64 10 to minus 7 seconds on average before emitting a photon and returning to the ground level. Part A. What is the energy of the photon in electron volts and what is its wavelength in nanometers? So when an atom makes a transition from a level above the ground level to the ground level, the energy difference is basically going to correspond to the energy of the photon that will be emitted. So we can write the energy difference between the first excited state and the ground level is 2.58 electron volts, and the time it takes for the electron to relax back to the ground level is 1.64 times 10 to minus 7 seconds. The ground state energy we can call 0 electron volts. Then the first excited state energy would be 2.58 electron volts. So this energy difference, delta E, between the first excited state and the ground level will correspond to the energy of the photon, which is hc over lambda, Planck's constant speed of light divided by its wavelength, is equal to 2.58 electron volts. And what will be the emitted photon wavelength? The photon wavelength in nanometers is hc divided by lambda is electron volts, so it's hc over energy. So this is going to be 1243 electron volts nanometers divided by 2.58 electron volts. So we can see that the wavelength will be 482 nanometers. Let's move on to part B of the problem. What is the smallest possible uncertainty in energy of the photon? Give your answer in electron volts. Heisenberg's uncertainty principle tells us that the uncertainty in energy multiplied by the uncertainty in the time of measurement is greater or equal to h bar, which is Planck's constant divided by 2 pi, over 2. So this is Heisenberg's uncertainty principle. With that, we can determine the minimum uncertainty in the energy, delta E minimum, to be h bar divided by 2 delta T. Okay, now we can calculate this. Delta E minimum is equal to h bar, which is Planck's constant h, 6.63 times 10 to minus 34 joule seconds, divided by 2 pi, but there's a factor of 2 here, so that's divided by 4 pi, and delta T is 1.64 times 10 to minus 7 seconds. So we're going to find the minimum uncertainty in the energy delta E minimum to be 3.22 times 10 to minus 28 joules, but we're asked to find it in electron volts, so divided by the electron charge, 1.610 to minus 19 coulombs, we will obtain 2.01 times 10 to minus 9 electron volts. So this is our minimum uncertainty in the energy of the photon that's being emitted during this process. Part C, show that delta E over E is equal to in absolute value, delta lambda over lambda in absolute value if delta lambda over lambda is much less than 1. Use this to calculate the magnitude of the smallest possible uncertainty in the wavelength of the photon. Give your answer in nanometers. Now, energy of the emitted photon is equal to hc over lambda. And if we look at a differential change in the energy, this is equal to, since it's a function of the wavelength, h and c are constants, the derivative of energy with respect to lambda multiplied by d lambda, and that's equal to minus hc over lambda square. Derivative of 1 over lambda is minus 1 over lambda square multiplied by d lambda. All right. Now, if I write dE divided by E, that is minus hc over lambda square divided by hc over lambda, so it's lambda over hc multiplied by d lambda. Now you can see here one of the lambdas will disappear and hc's will cancel out, and I will be left with minus d lambda over lambda. So this is for differential changes, and delta lambda over lambda much less than 1 basically ensures that this is a differential change. So we can write this in, for a macroscopic change, delta E over E is equal to, in absolute value, is equal to delta lambda over lambda. So with that, we can calculate the minimum uncertainty in the wavelength. Delta lambda minimum would be lambda times delta E minimum, minimum uncertainty in energy, divided by the energy E. This is how we calculate the minimum uncertainty in the wavelength. And once again, delta lambda over lambda much less than 1 is basically ensuring that this is really a differential change here. Okay, so we can calculate the delta lambda minimum. Delta lambda minimum is equal to lambda, which is 482 nanometers, times the minimum uncertainty in energy, 2.01 10 to minus 9 electron volts, divided by the energy, 2.58 electron volts. So that gives me, for the minimum uncertainty in wavelength, 3.75 times 10 to minus 7 nanometers. Okay, so we have an atom that has an energy level 2.58 eV above ground level. So let's call this the first excited state, 2.58 eV above the ground level. So if you have a transition uh, for an electron from this level to the ground level, there will be a photon emitted, and the energy of the photon emitted will correspond to the energy difference between these two levels, 2.58 eV. The wavelength of the emitted photon is basically determined by the photon energy equals hc over lambda. So this is 1243 electron volts nanometers divided by lambda in nanometers. So that's 1243 divided by 2.58, 482 nanometers. The minimum uncertainty in energy can be calculated by using Heisenberg's uncertainty principle. Delta E times delta T, the uncertainty in the measurement time, is greater or equal to h bar over 2. Now, on average, it makes this transition in 1.64 10 to minus 7 seconds. So that's the measurement time. So we have h bar divided by 2 delta t, the minimum uncertainty in energy, and we can plug in the numbers. Now, the energy of the emitted photon is hc over lambda. If I look at a differential energy, dE, by varying lambda, dE d lambda, that's minus hc over lambda squared d lambda, I find that dE over E is minus d lambda over lambda, or delta E over E is equal to delta lambda over lambda in absolute value. So the minimum uncertainty in wavelength is lambda times the minimum uncertainty in the energy divided by E. So plugging in the numbers, we obtain 3.75 10 to minus 7 nanometers.